Hello, I am Ayşe Duran from Kütahya Dumlupınar University in Kütahya in Turkey. I will talk about magnetic properties of manganese 3 gallium Husser alloys. And firstly, the presentation is outline the following. With why do we Husser alloys? We study Husser alloys. Critical structure of magnetic spin texture of manganese 3 gallium Husser alloy. Other theoretical method results and conclusion. So, we study Husser alloy. Husser alloys have been investigated a lot of paper and a lot of interesting properties such as magnetocaloric effect, thermoelectric, magnetocaloric effect, thermoelectric properties, phase transition, spin gapless, semiconductivity, half metallic behavior, magnetoresistance, spin polarization, superconductivity, shape memory effect, etc. These properties make them suitable potential conditions for future energy harvesting, spintronics, thermoelectrics, magnetoelectric technologies and applications have been designed, synthesized, modeled and analyzed by examining the change of physical quantities depend on temperature, pressure, magnetic field, etc. So, manganese-based alloys have been investigated, such as tunnel magnetoresistance, colloidal magnetoresistance, spin injection, spin torque device, and spin transfer switching. And manganese 2-based Husser alloys have alloys are in inverse L21, regular L21 tetragonal structures, and a lot of investigation. There have a lot of investigation, structural, elastic, electronic, magnetic, electrical, galvanometric, thermoelectric, seat preference, magnetostructural transition, magnetocaloric effect, that is dynamic properties, etc. We have studied manganese 3 gallium with L21 cubic structure. This is critical structure, and this article according to this article, we defined spin textures according the article. Gallium 1, gallium 2 spin up, manganese 1, manganese 1 2, spin up, manganese 2 spin down. Manganese 2 interact other magnetic atoms with ferromagnetic interactions. And we have investigated. We have in this investigation magnetic properties is manganese 3 gallium Höster alloy are explored theoretically by exploring Kaneshie approach in the framework of effective field theory, which has been succeed to model the magnetic properties of the magnetic system, such as this scene, as this scene, and effective field theory based on Ising Hamiltonian, and this in this structure we assumed that all of particles is spin half Ising particles. The Höster alloy has 3 states, 5 different magnetic atoms according to lattice location interactions in our model, and manganese 2, manganese 1, manganese 1, 1, manganese 1, 2, and gallium, this like. This equation is the Hamiltonian of Höster alloy, and say S3 plus minus 1 is the Pauli spin operator. H is the external magnetic field in Tesla unit. The exchange parameters are obtained by using the relation that G equal QOD in EV unit, where D is the real constant, D 5.82 angstrom of the Höster alloy, calculated theoretically by Woolman et al. Thus, the exchange parameters are calculated by as follows. This like this one, and Q1 Q1 shows ferromagnetic interaction, Q2 antiferromagnetic interaction. And by using Kaneshie approach, the normalized magnetization M, this where MT and MO show spontaneous magnetizations at temperature, and at T0 Kelvin, respectively, of the atoms of the Höster alloy are calculated by these equations. And total magnetization and the magnetization of it sits like this, and drag is the differential operator, and beta 1 divided to QBT. The function of f s half is defined by as follows. For the spin half using particles, this function and this H magnetic field, external magnetic field. We plot empty. We calculation the result of calculation as the result of calculation. We plot empty graph, and this manganese 1 artı this manganese 2 opposite sign alignment. So manganese exhibit ferromagnetic behavior. This gallium and empty manganese 3 gallium hoster alloy is not seen. This figure manganese gallium, manganese 3 gallium and gallium. Manganese gallium antiferromagnetic exhibits from antiferromagnetic to paramagnetic at 20.3 Kelvin, and we study magnetization versus external field of Hauser alloy, and on it sits at different temperatures, and at 1 Kelvin, this manganese 1 and gallium exhibit same hysteresis behavior, and gallium very weakly ferromagnetic. Manganese 1 ferromagnetic exhibit magnetic properties, and this figure, in this figure, we obtained critical fields, and critical field 1, 2, 3, and triple hysteresis behavior. This manganese 2 triple hysteresis behavior. This triple hysteresis behavior in manganese seat of the Hauser alloy is in a quality good accordance with the experimental hysteresis results of nickel and at nickel ferromagnetic gallium ferromagnet interface reported by Higgs et al. Epitaxial nickel X manganese 100 minus X single layers, and these layers reported by Makoto et al. And manganese film. This manganese film on copper reported by Reinhardt et al. Layer and nickel 50 manganese 34 tin 14 Höster alloy. And manganese 2 gallium Höster alloy triple step-like hysteresis behavior. Step-like hysteresis behavior low temperature. At low temperature is due to quantum tunneling of magnetization. This alloy this alloy can be used magnetic storage application and MH at 21 Kelvin. The triple hysteresis behavior go out. And step-like behavior is different. Another behavior and at 14 230 Kelvin, manganese 1 and gallium paramagnetic behavior, but manganese 2 and manganese 2 exhibit diamagnetism and vortex. We suggest there are vortex state and oops. 300 pardon, at 300 all of them paramagnetic behavior. In this result, as a result of MH plots. We plot phase diagrams, manganese Höster alloy and manganese for manganese 2. We suggested, according to literature, this phase diagram and in the state zero, 20 and 220, between 20 and 220 manganese 1 exhibit Meissner 2 vertex 2 surface and şöyle diyeyim. Until 101 Kelvin, manganese 1 exhibits Meissner 2 vortex surface superconductivity and normal state and below TC Meissner 2 vertex and normal superconductivity and TV vortex temperature, below TV vortex temperature, between TC/RT TV vortex to normals exhibit. Manganese 3 gallium Höster alloy exhibit other manganese, the difference of manganese 2 exhibit don't exhibit vortex to vortex. Okay, we have modeled and investigated the magnetic properties of manganese 3 gallium Höster alloy by using effective field theory. Manganese versus temperature plot in a zero magnetic field indicates that the alloy shows a second phase transition from antiferromagnetic to paramagnetic phase with increasing temperature. The current temperature is Tc of manganese 3 gallium is obtained to be 220.3 Kelvin. The phase diagram of Höster alloy and manganese 2 component are obtained and exhibit the phase states of type 2 superconductivity with surface superconductivity. Thank you.
Okay, thank you. Okay, if it is not the case, thank you again for your presentation.
I'm very excited. Sorry.
No problem, no problem.
Thank you.
Okay.